Chapter 1, we are getting close to the end, thankfully. We're going to talk very briefly, just this one slide, about intensive versus extensive properties. They are different. Intensive properties do not depend on the amount of substance. So if you have a little bit, the intensive property is the same as if you have a lot. So if I have the tiniest little bit, the intensive properties are going to be the same as if I have, 500,000 tons of the material. It's going to be exactly the same. So these are characteristic properties. So things like the density of a substance. If you have a small amount versus a big amount, those will still have the same density. They should have the same melting point. They should have the same color, boiling point. Other things are also going to be similar. And then we have extensive properties. These depend on the amount of the substance or the extent. Like if your house floods and somebody asks what was the extent of the damage, how much damage was done, what was the extent of the property, how much of the property do we have. So these properties are going to be things that you measure: mass, length, volume, things like that. If I have a small amount of feathers versus a big amount of feathers, small amount of feathers is going to weigh less than the big amount of feathers. And that's all we're going to really talk about for intensive versus extensive properties. I think it does come up a little bit. Probably shows up on the exam, which again, going to be pushed back almost definitely. Questions about intensive versus extensive properties. The other thing that comes to mind for me for intensive versus extensive, intensive, like intent, what you intend, what you mean. That's also not like a measurable thing, but I can't put into words how that connects with these being properties that can identify substances, things that aren't really measured. So if it connects with your brain, great. If not, that's fine too. We are going to now jump into just tons of calculation slides. I think we've talked about density. If we haven't, we'll talk about it briefly here. So let's say that a man receives a platinum ring from his fiancée. Before the wedding, he notices that the ring feels a little light for its size and decides to determine its density. He places the ring on a balance. He finds that it has a mass of 3.15 grams, so something we're given, mass of 3.15 grams. He then finds that the ring displaces 0.233 centimeters of water. And we want to know, is the ring made of platinum? So density is an intrinsic property, meaning that we can use it to identify what something is. The formula for density is density equals mass over volume. And realistically, you can use any units that you want, but also realistically, there's some units that we're going to use more than others. So oftentimes it's going to be grams for our mass, and then our volume will be something like milliliters, for example. Trying to swipe the wrong thing. Okay. So we've got grams, that's going to be our mass, and we've got this displacement. So it pushes out 0.233 cubic centimeters of water. That means that's the volume of the ring. We're going to be using this in lab today. This displacement method is nice because you can measure the volume of things that aren't a regular shape. So things like rings and blobs of metal, chunks of metal can be measured nicely this way. So that's our volume. And cubic centimeters, cm to the third power, is the same as milliliters. Okay, so calculating our density of our platinum ring, density equals 3.15 grams divided by 0.233, changing it to milliliters. Both of those have 3 significant figures, so the fewest significant figures is still 3. So we're going to have 3 sig figs for our final answer. Calculator says that our density is 13.519 and some other stuff. That would have units of grams per milliliter. Third significant figure is the 5. The 1 tells us that we round down. So 13.5 grams per milliliter. Is it platinum?
Depends. We'll compare it with whatever platinum.
We'd have to look up what is the density of platinum. There's probably a table in our book that has it. I'm just going to rely on Google. Google says the platinum density is 21.45.
It's not.
So platinum PT is 21.45 grams per milliliter, and hopefully that's correct. It seems to confirm, so AI is not making stuff up. What's our final answer for this question?
No, it's not platinum.
Yeah, the final answer is no, not platinum. We can't say what it is, but we can say it's definitely not pure platinum because the density would match if it was pure platinum. Or if it was a mixture of platinum and something else, then it should match, or at least more closely match our density. So it's probably not platinum, just based on the density. So the woman in this example is shocked that the fake ring is fake and returns it. She buys a new ring that has a mass of 4.53 grams and a volume of 0.212 cubic centimeters. Is the new ring platinum? So go ahead and try doing the calculation and see whether it's platinum. All right, let's find out if the new ring is pure platinum. It's also nice that the fake ring was able to be returned. That's often not the case. So that's a little surprising. So density equals mass over volume. Our mass is 4.53 grams. Our volume is 0.212 cubic centimeters, which is the same as milliliters. Again, these both have 3 significant figures, so 4.53 divided by 0.212. Calculator says 21.3679253 grams per milliliter with 3 significant figures. Okay, so 21.36, the 6 says that we round up, and so it's going to be 21.4 grams per milliliter based on our calculations in Google. We had previously determined, said 21.45 grams per milliliter. These are close enough that we can't really make a distinction based on our measurements. If we got better measurements, then maybe. But these are essentially identical for our purposes. Very close, probably platinum. It's possible that our volume measurement was a little bit off. It's possible that our density measurement was a little bit off. If we were concerned that it's not platinum, this is a good sign that it is probably at least mostly platinum, but we could take it to a different jeweler maybe and have them test it with different methods. And that might give us a better idea of whether it's platinum or not. Okay, other density stuff. The density of copper decreases as temperature increases, as does the density of most substances. Which change occurs in a sample of copper when it is when it is warmed from room temperature to 95 degrees Celsius, which is way higher than room temperature? Does the sample become lighter? Does the sample become heavier? Does the sample expand? Does the sample contract? What do we know is changing for sure? The temperature. And what else changes because of temperature? The density. So as temperature increases, the density changes. So temperature increases, density decreases. And what are the two factors in density?
Mass and volume.
Yeah, density is mass over volume. If density is decreasing, how would these two things be changing? How would mass change to make density smaller?
Mass.
If mass decreases,
The volume would increase.
then density would decrease if it takes up the same amount of volume. Alternatively, for volume, volume could change. How would volume change to make density smaller?
Increase.
Yeah, it would have to increase. So mass could decrease, volume could increase. So that removes two of our options. The sample becomes lighter, mass going down. That could be an option that would change density. Our other option is based on the volume. The sample expands would mean that the volume gets bigger, and so that could be true just based on how we know density is changing. Now, for heating something up, do we think that the sample is becoming lighter, or do we think that it is expanding? Which one do we think is more likely?
It shrinks. Oh, when you heat it up,
It
volume
expands.
expands.
Yeah.
It gets bigger.
So based on these two options, we're not changing the amount of matter that's there, right? Because it's still the same mass of copper. It's not like it's boiling away. So it's the same amount of copper, so it's got the same mass, so it's not going to become lighter.
So when it's cold, it shrinks.
But it is going to it's going to expand. And yes, if you cool something down,
It shrinks.
then it will shrink, generally. Yes?
Can mass increase and volume decrease, or it's just mass when, yeah, wait, no.
So
Can it be opposite, like
if we
density-
switched one of the arrows, the other arrows would switch.
Oh.
Yeah. So if density was increasing, then these arrows would also flip. So generally, when you heat things up, they expand, and generally, when you cool things down, they contract. So sometimes, like in the lab, people stick two beakers together, a couple pieces of glassware together, and they get stuck together. And one of the ways that we can get them unstuck is by heating the ring, heating whatever's on the outside, and that causes the glass to expand, and then we can pull out the beaker that's stuck on the inside. There's also like, if the lid of a jar is stuck, you can also heat up the lid of the jar, and sometimes that gets it to expand enough that it's not clamped down so hard, and then you can remove it without needing to break out some special tools or possibly break the jar. Okay, in chemistry, we're going to be doing a lot of unit conversion problems, both in terms of just doing them as pure unit conversion problems. We'll also require some specific equations. Many of those, the first time that we encounter them on an exam, you'll be given the equation many times. Other times, you'll have to memorize them. I think for this class, I usually give equations the first time that we encounter them on exams. And then a lot of the problems I'm going to frame as unit conversion problems. And we're going to use our units as our guide to solve our problems. And this is called dimensional analysis. The dimensions are just the units. So dimensional analysis is just unit analysis, unit problem solving. We are going to treat our units like part of our numbers. They're always going to get included. Always write your units. This is crucial. This is not fun initially. You'll be a little bit annoyed. You're going to want to skip writing your units out. Once you get the hang of it, once you get used to writing your units, it's not a big deal. So stick with it. You'll get used to writing your units, including in every single step of every single calculation. I'm going to do this throughout the course. And that can save you sometimes, especially on exams, especially on free response questions, because you might see, oh, I put the units in wrong, or I put my conversion factor in upside down, and then you can switch it so that you get the right units out. So we always want to include our units. We're not going to magically make them appear. We're not going to magically make them disappear. And we're also going to treat them like algebraic quantities, things like x, y, z, variables. So for example, if we do x times x, that would turn into x squared. We could also expand x squared out to x times x. Similarly, if we were doing some area calculations, and we've got two measurements in centimeters, we multiply those centimeters together, that would turn into centimeters squared. There's another property that we can take advantage of. If you've got one thing on the top and you divide it by something with the same units, those units disappear. So for example, this conversion factor that I'm sure we'll see here soon, if we want to make a conversion factor out of this, we move something from one side to the other. I'll just divide both sides by the inches because it's shorter. So if we treat both sides equally, divide both sides by 1 inch, this left side 2.54 centimeters over 1 inch, the right side 1 inch over 1 inch. Since we've got inches on the top and inches on the bottom, those inches cancel out. The ones also divide out, so that whole right side turns into 1. The units disappear. So that's a way that we can get rid of units, is if we're dividing by them. And so we're often going to use our conversion factors strategically to either get rid of inches in this case, or if we flipped the top and the bottom, then we'd be getting rid of the centimeters. And we'll see that we've got a bunch of calculations that we'll be doing today. All right. A unit equation is a statement of two equivalent quantities, any two units, any two things that are the same. We've got many of them on our yellow sheet. So if you're looking at your yellow sheet, on the left side, the first column is our unit. So looking at the top row under distance, 1 meter. And then over 2 columns, definition or equivalent, 39.37 inches. So 1 meter equals 39.37 inches. Sometimes you'll also see these written out in tables like for pressure. Just to give you an example, you don't need to know this yet. But it might give us multiple units. So like it would give us, let's say, mmHg, millimeters mercury. It would give us a value of 760. Atmospheres, it would give us a value of 1. So we'd pull out any of the two things. There'd be more in there. So we could pull out like mmHg at 760. That's equal to atmosphere, which would be 1. So 1 atmosphere equals 760 millimeters mercury. And I'll talk about that when we get to it later, I'm sure. Okay, so conversion factors. We looked briefly at that. Previously, there's 2 ways of thinking about writing them, but there are going to be fractions. It's going to be a ratio of 1 unit on top to another unit on the bottom. So we want the unit we're converting from on the bottom, the one that we're getting rid of, or the one that we're starting with, we want on the bottom, and the unit that we are converting to, or that we're trying to get, we want to put on the top. So if we're using this 2.54 centimeters equals 1 inch, there's 2 conversion factors that we can make with this. In algebra, if we treat both sides the same, then we've changed nothing. So we can divide both sides, or multiply both sides, or add both sides, whatever we want. And as long as we do it equally, nothing's changed. And we can use that to get rid of the centimeters, to move it over to the other side, or we can move the inches over, like we did here. So we wanted to move the inches over, so we divided both sides by 1 inch. The right side turns into 1. The left side then is our conversion factor. And the shortcut for this is that you take something from the top on one side, and you can move it to the bottom on the other side. So this would turn into 2.54 centimeters over 1 inch. If we wanted the centimeters on the bottom instead, then we would get 1 inch over 2.54 centimeters. So those would be our two possible conversion factors based on those two things being equal to each other. Yeah, so another cool thing about these conversion factors, you can make one form, and then if you notice, right, the first form we've got the 2.54 centimeters on the top, the other one it's on the bottom. The first one, 1 inch is on the bottom, the other 1 inch is on the top. So another thing, you can make a form of a conversion factor, and then if you want to, you can flip it for free. And this comes from the fact that these are both equal to 1. And so you can take the inverse of 1. 1 over 1 is still 1. And because these are equal to 1, when we multiply by these conversion factors, we're multiplying by 1. When you multiply by 1, nothing changes. So that's sort of like the behind-the-scenes math secret for why this works and how we can do it, why we can do it. A lot of our problems, our very simple unit conversion problems especially, are going to have the following form. We'll have some information that we're given in a problem, and I'm usually going to underline that in green. We'll also have some information that we are looking for, or the answer, or what we're asked to find. And I'll usually underline that in this pink or fuchsia. And then we may be given conversion factors. Those usually get blue or get written in as blue. Sometimes we'll have to go look up conversion factors, or we'll have to know them. So that's where the yellow sheet can come in handy. So we'll take the information that we're given with whatever units we're given. We'll multiply by the conversion factor. And the conversion factor, we want the units that we are given on the bottom. That way we've got one set of that unit on top, another set on the bottom, and those cancel out in terms of units. And then the unit that we want, being on the top, comes out after the equal sign. So as an example, how many centimeters are in 12 inches? So we are given some information. A lot of the time that we're given a number, that's information we're given. So 12 inches, that's some given information. And what are we being asked to find? Centimeters. Usually the information that we're asked to find is right next to a question word in the problem. So question words being like who, what, when, where, why, how. Something like that. Something that indicates that that sentence needs a question mark after it. It won't always be there, but oftentimes we'll have question words. And the reason that I point that out is some of the sentences, like in the problems that we'll be given, the word problems that we have, sometimes it looks like they're written backwards, and so identifying where a question word is can help us figure out what we're actually finding, for those of us that aren't quite so good at word problems. Okay, so we were given 12 inches, and we want to convert to centimeters. Our relationship between inches and centimeters, 2.54 centimeters equals 1 inch. So when we make the conversion factor, we're starting with inches, and so we want the inches part of our conversion factor to be on the bottom. So divide both sides by the inches part. We're going to have 2.54 centimeters over 1 inch. If you don't like thinking about what we're getting rid of, you can also think of what we're going to. That also works. It gets you the exact same outcome. So we want to get centimeters out. Centimeters goes on top. That means the inches would go on the bottom. And I usually write things out with this big line going between the top and the bottom, and then these vertical lines just separate out our terms. So our given information is always on the far left, and then we can stack up as many conversion factors as we want after that with those vertical lines separating them. It just helps me keep my work nice and tidy, and that's the way I've been doing it for a while. Okay, so since we've got inches on the top and inches on the bottom, those will cancel out, so we'll give those a slash through. The units that are left are centimeters, and so those come out at the end. So 12 times 2.54 is 30.48 centimeters. We were given 12, that's two significant figures, so we'll round this down to 30 centimeters. Or if we wanted to, 3.0 times 10 centimeters to put it in scientific notation. General problem solving strategies, use some of those in there. So we want to identify our starting point, our given information. I usually underline that in green in the slides. And oftentimes we'll want to write down our given numbers with their units. So you might collect all of your given information, pull it out to the side at the start of your problem, just so that you know all the tools that you have to work with. And if you see per, this usually means divides by or divided by. For example, miles per hour is miles over hours. So sometimes we'll see it written in as per, and that means that it's one thing over another, and these can often be used as conversion factors because we've got one unit on the top and another unit on the bottom. Miles per hour probably not going to be used as a conversion factor, but there might be other weird things that we come up with that have per involved in them. And then we want to identify our endpoint or our find variable, usually next to a question word, as mentioned on the previous slide. Not always, sometimes it's just calculate this or find this, but oftentimes it'll be next to a question word. And then we want to put together a solution map, draw up a plan for how to get from what we were given to what we were asked to find. So from our given to our find, the conceptual plan here might include conversion factors, stoichiometry, which we'll talk about later in a later chapter. And it could also have something else in there, like equations might show up. And that can be multiple steps. At its simplest, it's going to be one step. Other times later in the class, it might be 4 or 5 steps, potentially. And that's especially where we want to include all of our units, because we'll have a bunch of different steps that we need to do. We want to make sure that we're adequately crossing them out, canceling them out, and bringing in the new units as well. And then once we've got this plan drawn up, and this plan usually, we're not plugging stuff into the calculator yet, we're just writing all the numbers out, writing our conversion factors. Once we've done this, then we can solve it. So we can follow the plan that we made, step by step. We can do it in a calculator. Sometimes you might want to do it twice, depending on how competent and confident you are with your calculator. And you'd also want to check and make sure that your units are correct. And that's something that we would do in this step 5. So we can check, does the answer make sense? Like, does the size of the number make sense? Or is it reasonable? And then also, are the units correct? Wrong units means the wrong answer. So even if you did everything correct, and it's technically true, if it's not the correct answer, or if it's not in the correct units, then it's not the correct answer. Sometimes on short answer problems at the end of the exam, I won't tell you what units to put it into, and so you can kind of pick whatever units you want. Oftentimes, though, especially on the multiple choice, there are units that it asks for, and if you give it in the wrong units, that's probably going to be one of the options, and it'll also be incorrect, just like the number in those units. An example of the size being reasonable, I'm about 6 feet tall. I'm a little shorter than 6 feet, so I'm like 5'10". If I was converting my height into meters, because I'm talking to someone who's not in the US, I'm going to just round up and say that I'm 6 feet to make it easy. Meters, or 1 meter, is about 3.3 feet. So I know there's a 3.3 in there somewhere. Let's say I don't write out the units. I do 6 times 3.3, and I come out with 19.8. And we just tack meters on there. So if I tell somebody that I'm 19.8 meters tall, does anyone think that that's true? No, I'm definitely not 19.8 meters tall. For reference, right, a meter is about the same as yards, so this is 2 first downs. I'm not 2 first downs tall. I'm not a fifth of a football field long, right? 20 meters is probably the length of the class, the width of the class. So that would be like, oh, 19.8 meters for how tall Mr. K is? No, that's definitely wrong. And so that sense of, does it make sense? Is it reasonable? That's what we're doing at this check step. Does the answer make sense? For a lot of the things in the class, you are not going to have a sense for if it's reasonable or not. But the more that we do these problems, you'll start to build up a little bit of an is that reasonable or not sense. So the real solution would be, again, about 6 feet. 3.3 feet would go on the bottom, and 1 meter would go on the top. The feet cancel. So it'd be 6 divided by 3.3-ish. So it'd be around 1.8 meters, which for sig figs would turn into 2 meters, which, again, I'm definitely not 2 meters tall, but that'd be a much more reasonable answer than 19.8 meters. Questions about any of that so far? Cool. Let's say that we want to convert 288 centimeters to yards. What are we given? Yeah, we're given 288 centimeters. What are we asked to find? Yards. So we are going from centimeters to yards. Can we do that in one step? Probably not. There's a way that you could do it in one step, but that's probably not a conversion factor that we have access to immediately. What's something that we can convert centimeters to?
Inches.
Inches. Can we convert from inches to yards?
12, isn't it? Was it 12 inches then? 1 yard?
It's 12 for a foot, so we can go to feet. Can we go from feet to yards?
Yeah, 3.
Yeah, we can. So this would be our solution map. This is our map of what our units are going to do at each of our steps. Each of these arrows represents either an equation or a conversion factor. In this case, it's conversion factors. So there's 2.54 centimeters in 1 inch. There's 12 inches in 1 foot. And there's 3 feet equal to 1 yard. You don't necessarily have to write them out as this thing is equal to this thing. If you know what the conversion factor is going to look like, you can write it in that way right out the gate. Okay, so we've collected all of the pieces of information that we need. We're starting with 288 centimeters. And we're going to do 3 steps. So we're expecting 3 conversion factors. Our first one is this 2.54 centimeters is 1 inch. We have centimeters, so we need the centimeters to cancel, so that means the centimeters part goes on the bottom. So divide by 2.54 centimeters, multiply by 1 inch. And if you want to, we can keep track of our units as we go, so we can cancel out the centimeters. And if we look at what units are left, we've got inches. That's where we're supposed to be based on our solution map, so we're on track. Okay, second conversion factor. 12 inches equals 1 foot. We have units of inches, so we have to get rid of those units of inches to turn it into feet, so the 12 inches part goes on the bottom. So divide by 12 inches, 1 foot goes on the top, and our units of inches are going to cancel from our first conversion factor to our second conversion factor. Units that left are feet, or that are left are feet, so we're on track. And we've got one more step. It's the 3 feet equals 1 yard. Again, we're dividing by 3 feet to get rid of the feet, so that we've got 1 set of feet on top, 1 set of feet on bottom. Those will cancel, and then the 1 yard part goes on top. So cancel out the feet. The units that are left are yards. That's what we were asked to find, so that's a good sign. That means that we hopefully didn't screw anything up, as long as you had your numbers correct with the units that they go with. If we got some nonsense units out here, like if we got inches per centimeter or something like that out at the end, that would be a sign we did not set it up correctly. We would need to flip some conversion factors. So if you end up with nonsense units at the end, that's a sign you need to recheck your work. Notice that we did all of this before we touched our calculator. So this lets us catch some unit errors before we even plug stuff in. Sometimes our inclination is just to start plugging numbers in and then press enter and hope that's the right thing. But then we wouldn't necessarily have this work to check. And on short answer questions on exams, if you show the work and somehow fumble the calculation, you can still get most or all of the points if the work is correct. So that's another reason why it's good to show our work. So what we're putting into our calculator, we multiply everything on the top. So 288 times 1 times 1 times 1, that's 288. Some of you might want to separate these, do these separately. I know that some people do the top, and then they'll multiply everything that's on the bottom. So 2.54 times 12, I missed a number, times 3. So on the bottom they would get 91.44. And then you can put those into your calculator and get an answer out. And that number would be 3.149606. But wait, there's more. 299 yards. And how many significant figures should we have? 3. We had 3 from our starting number. Our first conversion factor, this one's secretly an exact conversion factor. It says that on your yellow sheet as well. So that's infinite sig figs. And then these other two, 12 inches and 1 foot and 3 foot and 1 yard, those are in the same system, the English system, and so those are also exact. So the fewest between 3 and infinity is 3. So we'd round for 3 significant figures. Our answer that we report, 3.15 yards. Any questions about that? Cool. Now I'll give you one to try. Convert 9,255 cubic centimeters to gallons. And I'll just go ahead and remind you that cubic centimeters are the same as milliliters. All right, converting cubic centimeters to gallons. We're starting with cubic centimeters. That's what we're given. We're converting to gallons. So cubic centimeters, which are the same as milliliters. So I'm just going to swap it out to milliliters. From milliliters, we can go to liters. And from liters, we can go to gallons. We're given one of the conversion factors up here in the top right, 1 gallon, 3.785 liters. Since we'll have liters at this point, we want the 3.75 liters part to be on the bottom. So you can just jump to the conversion factor form that you need if you're confident that you're doing that correctly. So 1 gal over 3.785 liters. And then for milliliters, the milli prefix equals 10 to the minus 3. So 1 milliliter, if we swap out the milli prefix for 10 to the minus 3, then this is equal to 0.001 liters. Alternatively, 1,000 milliliters equals 1 liter. Those are the same, just different where you put the number into your calculator. Okay, so I like this red one better, 1,000 milliliters and 1 liter. We have milliliters, so the 1,000 milliliters is going to go on the bottom. So 1 liter over 1,000 milliliters. And then we set up the calculation, 9,255 cubic centimeters. Again, that's the same as milliliters. And then our two conversion factors. We've got milliliters on the top as well as on the bottom, so those cancel. And then our second conversion factor, 1 gallon over 3.785 liters. And the liters now cancel. And we're left with units of gallons. That's what we were asked to find, so that's a good sign. So into our calculator, 9,255 divided by 1,000, also divided by 3.785. Calculator says 2.4451. Keep forgetting that I write everything out. 517,836 gallons. We're going to round it to 4 significant figures, since that's what we started with. And that's also what our gallons to liters conversion has. So 2.445, the 1 means that we truncate, so we just drop everything after that 5. So final answer, 2.445 gallons. Any questions? Cool. Conversions with metric prefixes. So we can easily make conversions between a base unit and the same unit with a prefix, so add a prefix onto it. For example, 1 kilometer or kilometer equals how many meters? So the prefix, the kilo prefix, whatever our prefix is, has a number value that it's equal to, like we saw in that previous slide. So we would look up, what is that prefix equal to? Kilo is equal to 10 to the 3, which is the same as 1,000. So we can substitute in, for this kilo, we can put in the number version. We're going to write the number on the other side. So 1 kilometer is equal to 1,000 meters. The prefix goes on one side, the multiplier, or what the prefix is equal to, goes on the other side. So we'll end up with one side that's got the prefix, and the other side will have a number that goes with it. If both of our units, so if we're starting with units with prefixes and we're going to units with a different prefix, usually it's most straightforward for us to do that in 2 steps. It's less likely that we're going to get messed up or ruin our the way we've set things up. So, for example, converting from centimeters to nanometers, we can convert from centimeters to meters, and then from meters to nanometers. So we'll need 2 conversions. This isn't strictly necessary. You can go directly from centimeters to nanometers, but it is helpful to do it in 2 steps instead. So 1 centimeter, what's the centi prefix equal to?
100. Centi. Wait.
1/100th. So the exponent form is 10 to the minus 2, so it'd be 10 to the minus 2 meters. If you know how many centimeters are in a meter, you could also do 100 centimeters equals 1 meter. That's what I do in my brain, but I'm going to erase that because you might not do that in your brain. So the surefire way is we plug in what the centi prefix is equal to. So 10 to the minus 2, or 0.01 meters. And then our meters to nanometers, we would need to know what nano is. So 1 nanometer, the nano prefix is 10 to the minus 9. So it'd be 10 to the minus 9 meters, or I'm not going to write it out in standard notation because that's too many zeros, but there would be 0.801 meters. So starting with centimeters, we take the centimeters part and put that on the bottom, so the 1 centimeter goes on the bottom. The 10 to the minus 2 meters goes on top. And that converts away the centimeters. And then with the nanometers part, we've got meters now, right? 10 to the minus 2 meters. So we take 10 to the minus 9 meters, put that on the bottom. The 1 nanometer part goes on the top. The meters cancel. We'd be left with units of nanometers. So that might be how we would set this up, just as an example. Questions about making our conversion factors for metric prefixes? You probably took Chem 20 before this, so I'm assuming that we have already done this before. If you're confused, though, feel free to ask questions in office hours, during class, or during lab. All right, let's say we want to convert from liters to milliliters. This is a metric prefix problem. So we can do it in 1 step. The first one's meter or liters, the second one's liters, but we've got a metric prefix on there. So we need to know what is milli equal to.
1,000.
Milli has 1,000 related to it. So we would take the milli side, right, 1 milliliter, and that's equal to, what is our prefix value? 10 to the minus 3. So we looked that up, 10 to the minus 3. That swaps out for the milli. So 1 milliliter is 10 to the minus 3 liters. We're starting with liters, and so we want the liters part to be on the bottom for our conversion factor. So that looks like, starting with our liters, the 1 milliliter on top, the 10 to the minus 3 liters on the bottom. And our liters that we started with are going to cancel out with the liters from our conversion factor, which is a good sign. Okay, so we're putting in 0.00423 divided by 10 raised to the power of -3. And you should get 0.423 milliliters. There are a couple of things that I can imagine going wrong when you put this in your calculator. So, a couple of ways to put it in. If you get syntax error, that's one of the ways that I would imagine that things got messed up. So we divide by, and then on my calculator, there's a button that we're going to press. The button has a little E with a box, and then 10 with a little box, and that's all on one button. If you have that button, if you press it 2 times, then it'll give you that, what we want, which is the 10 with the box above it. So 0.00423, hit the divide sign, that'll put in this slash. Hit that button twice, and now we've got 10 with a little box, and we should be hovering in that box. So 10, and then in our little box, we want to put -3. And that is the wrong answer.
Yeah.
Okay, great. That's not how I put it in the first time. Troubleshooting. Did I put it in wrong? Oh, I put it in wrong the first time. Yeah, okay, cool. I was wondering about that. Great. So it's not wrong, it was wrong before. 4.23 as a brain issue on my part. Okay, 4.23 milliliters. So you divide by 10 to the -3, and it should give you 4.23. So this E key is what we're using to enter the 10 raised to the power. And then for this minus, it's different from subtract. So on my calculator, it's a minus sign inside of parentheses. Down by the enter key, that's the one that you have to put in for the minus. And that should resolve your syntax error. There's other ways of putting it in that I'll talk about maybe later. Questions at all? Cool. This is an extra example. I'm not going to do it. If you look at the lecture slides, though, the answer should be under this red block. They won't show up on the unannotated notes. But that'll involve centi, which is 10 to the -2, and micro, which is 10 to the -6. That's so that we can get to units raised to a power. So sometimes we will use units raised to a power, thinking specifically of things like cubic centimeters or squared centimeters. Question?
For the transition of the units, do we always have to use the prefixes for the metric system? We can use like the units already that we know. Like, maybe you can scroll up just real quick.
Here?
Yeah.
There.
You know how 1,000 milliliters is 1 liter?
Yeah.
Will we be able to put that on top and then 1 liter on the bottom, just like that, and we'd be fine? Or?
Yeah, so if you know that 1,000 milliliters is equal to 1 liter, you can use that instead.
Oh, okay.
It's mathematically, it's identical. Just this way always works, and just knowing the units doesn't always work because many of us don't just know the units. But if you know that 1,000 milliliters is 1 liter, you can just do that instead. Yeah. You should get the same answer. All right, so units raised to a power. This is also a place where we can run into issues. So if you've got a unit raised to a power, so it's got an exponent on it, when we're making that conversion factor, you can either, there's a couple of different things you can do. One of the ways is what we're showing here. So you can raise both the number and the unit to the power. For example, if we're doing an area calculation, we've got inches squared and centimeters squared. 2.54 centimeters equals 1 inch, but we've got squared units, and so we need our conversion factor to have squared units as well. And so what we're doing from this first step to the second step is we're squaring both sides. So we take the left side, we put it in parentheses, and square it. The right side in parentheses, and you square it. And then because that square is applying to the whole side, we can distribute that square. So now instead of it being over the whole thing, it's 2.54 squared centimeters squared. So the squared is applying to both things. And it's the same idea on the right side. The squared is applying to the 1 as well as to the inches. So we get inches squared and centimeters squared. Those are the units that we wanted. And 1 squared is equal to 1, so that doesn't change. 2.54 squared is apparently equal to 6.45. What would I call this? We'll just say do the math. Evaluate is what I was thinking of. And then this is our new two things that are equivalent. It's the squared addition. So we take the 6.45 centimeters squared divided by 1 inch squared, and that would give our conversion factor from inches squared to centimeters squared. That's one of the ways that we can do it. If we were cubing it, so if we had cubic centimeters or cubic inches, instead of squaring it, we would cube it, so raise it to the power of 3. And that'll follow the same steps. For example, how many cubic centimeters are there in 2.11 cubic yards? So 2.11 cubic yards. Cubic yards is often what you buy, like potting soil is often measured, I think, in cubic yards or cubic feet. I don't remember. It's been a while since I've been to the potting store, the nursery, to buy potting soil. So we want to go from cubic yards to cubic centimeters. Cubic centimeters is going to be cm raised to the 3. So starting with yards raised to the 3rd power, what's something that we can convert yards to?
Feet.
Feet. We could also skip a step and go to inches.
Mm.
So I'm going to do that.
Okay.
So 36 inches equals 1 yard. Just combining 3 feet in a yard and 12 inches in a foot. And then we can go from inches cubed to cubic centimeters. And our base for that, our base conversion is 1 inch equals 2.54 centimeters. So the first step I'm going to show you like we did on the previous slide. So the first thing that we want to do is we want to cube both sides. Then we can distribute the cubes. So the power of 3, so 36 to the 3rd power. It's a weird looking 3. And inches to the 3rd power equals 1 to the 3rd power times yards to the 3rd power. And then we can take these cubes and apply them. So for the 36, 36, raise that to the third power. That is equal to 46,656 with units of cubic inches, and this is equal to 1 cubed, which is 1, and cubic yards. So that would be our first conversion factor. And doing it this way is nice because it doesn't take up as much room, believe it or not. The other way that we can do it, I'll show you in a sec. So starting with our cubic yards, we figured out our conversion factor is that there's a heck of a lot of cubic inches in 1 cubic yard. So we'll write that number in, cubic inches over 1 cubic yard. We've got cubic yards on the top and on the bottom, so those will cancel all in one step, which is great. Now we've got cubic inches, and we want to go to cubic centimeters. We can use the same process as we just used, or there's another way that we can do it. What does the 3 mean here? Cubed, which means what?
Centimeters.
It means that it's multiplied by itself 3 times.
Right.
Right, so cubic inches is the same as inches times inches times inches. So we've got 3 sets of the unit inches in there. We can, if we wanted to, which I'm going to do this time, we can cancel each of those out individually. Each of these units of inches is going to take 1 conversion factor, though. So if we apply this conversion factor 3 times, it'll cancel out the inches. So since we have inches, we need the inches to be on the bottom, the centimeters will be on the top. So our first is going to look like this. And we're dividing by just 1 unit of inches. So this 1 unit of inches is going to cancel out 1 of these units of inches. So cancel that out, and this 3 turns into a 2. We have to apply it 2 more times. So another 2.54 centimeters over 1 inch. And then another time, and unfortunately my nose is starting to run. Okay, and these other 2 inches are going to cancel out the remaining parts, and we'll end up with cubic centimeters. Questions about the process? I trust that we can do the math to find the answer. Okay. So the way that we showed on the previous slide is nice because it's more compact, but you can also do it stepwise. Just don't forget that you have to apply it the same number of times as you have the exponent there. And there's some more examples. Let's go ahead and just do one of these, density as a conversion factor. So backpackers often carry around little canisters of white gas or propane or alcohol to fuel a cooking stove's burner. If 1 canister contains 1.45 liters of white gas and the density of the gas is this, what is the mass, or question word, what is the mass in kilograms? Okay, so starting with, what do we think? We've got 2 things that we were given. What's one of them? We were given liters. We were also given density. Typically, I like to start with the simpler unit. So 1.45 liters is just 1 unit. Grams per cubic centimeter is 2 units. So I want to start with liters. And we need to eventually get this to kilograms. Cannot do this in one step. What is something that we could use to get kilograms? grams. We can go from grams to kilograms. 1,000 grams is equal to 1 kilogram. How would we get grams? What has grams in it? What's something that we have that has grams in it? The density. The density has grams in it. What's the other part of it? So we've got grams, but we also have what?
Centimeters, which is also milliliters.
Centimeters. Yeah, cubic centimeters, which is the same as milliliters. Can we get from liters to milliliters? Sure can. 10 to the minus 3 liters equals 1 milliliter. Okay, so this middle step, this cubic centimeters or milliliters to grams, we're actually using our density as a conversion factor. This density value says that 0.710 grams is equal to 1 cubic centimeter. Okay, so our calculation looks something like this. This isn't the only way you can do this, but this is one way to do it. 1.45 liters, our 1 milliliter goes on the top, 10 to the minus 3 liters on the bottom. Now we've got milliliters. Milliliters are the same as cubic centimeters. In our density value, cubic centimeters is on the bottom. So if we just apply it, the 0.710 grams would go on top. The cubic centimeters, which is the same as milliliters, goes on the bottom. And so our milliliters will cancel. This is why we can use it as a conversion factor, because it's got 2 units in there. So this will convert us to grams. And then at the end, we can convert to, the last step, we can convert to kilograms. So 1,000 grams on the bottom, 1 kilogram on the top. And our grams will cancel, be left with units of kilograms. Questions about any of that setup? Okay, we should get out for our answer with 3 significant figures. 1.03 kilograms, assuming that I did all that calculation correctly. All right, and then I'm not going to cover the rest of chapter 1 because we're kind of behind. So we'll start chapter 2 next class.